Good morning, everyone. Welcome to lesson number 6. Today, we're going to start our study of nuclear physics. If you are a junior or interested in taking a quiz for fun, there's a quantum check for understanding quiz today that is due before next class. It's on goformative.com, and magically through the connection between the Google Classroom and goformative.com, you already have an account. All right, so give that a try and look on the Google Classroom for more info. Today, we're also going to start the nuclear physics portion of our modern physics unit, and we'll look at that Rutherford Goldfoil experiment and talk about how we use conservation of energy to determine the radius of a nucleus and a nucleus's density, and defined what's called the atomic mass unit. And then you're going to, as homework, investigate relationships in nuclear decay. Okay, let's get started. All right, so before we move forward, we do need to give ourselves a reminder about some abbreviations, really, that are related, that are related to how we represent an atom and what it's made out of. Okay, so I'm going to remind you of how we abbreviate an atom. Okay, so let's pretend that this X is atomic abbreviation of some sort, right? So it could be Fe for iron, H for hydrogen, whatever. I'm going to draw it as a generic X. Up here in the top left corner, there's a number that goes there that is abbreviated with a capital A. So the number that goes up in the top right corner is called the mass number. And it's the number of protons and neutrons put together in an atom. Okay, and then down in the bottom left, we've got a number that goes there in this symbol. It's typically abbreviated with a capital Z, and this is called the atomic number. Atomic number, and that's just the number of protons, because they're not always equal. Okay, all right, and then I don't know if this is used in chemistry much, but in physics we call any particle in the nucleus a nucleon. Right, a particle contains in the nucleus. Right? So we could say, like, if something had 2 protons and 2 neutrons, right? Like a helium nucleus, there would be 4 nucleons. All right, so next let's take a look. This is how we can represent atoms, right? But we can also use this to represent individual particles that exist within an atom. So I want to give a graphic for some common ones here. All right, so sometimes we're just talking about a proton, right? So we could write P as the abbreviation for a proton, and then a proton is 1 nucleon, and it is 1 proton, right? So you'd write it like that. A neutron is 1 nucleon, no protons. An electron is not a nucleon at all. And this is a little bit hairy, but we give it a -1 because it has the charge of a proton, but it's negative. Okay, so that's how we represent an electron. And then there's a photon, which is not a nucleon, it's not a proton, it doesn't have any mass at all, it doesn't have any charge. And so this is how we abbreviate it. This symbol is a lowercase gamma. In my handwriting, I tend to write it like that. Let's see if I can do it better. Yeah. So that's just the way I write it. It looks more like a curvy Y sort of deal in typeface, but just so you can interpret my handwriting versus typeface. And then an alpha particle, remember, is a helium nucleus with 4 nucleons, 2 protons, 2 neutrons, right? 2 protons. Or we can write it as just an alpha. It's a common particle that's used as an alpha particle. And an alpha, right, it's like the little fish guy here. It's the lowercase Greek letter alpha. So we use that. It's the same thing as a helium nucleus. 2 protons, 2 neutrons. All right. What's holding the nucleus together? Where there are a bunch of forces, and there are 3 that are working to hold a nucleus together. And sometimes some forces are working against each other. And that's one of the things that we're going to investigate is, when do nuclei come apart? Like, under what circumstances? And are there any patterns? All right, so the first force that we know about that acts within a nucleus is the electromagnetic force, right? The electromagnetic force acts on charge. That's modeled by electrostatic force equals K times Q times like Q1 or something times Q2 over R squared. Okay, I was literally teaching this yesterday to the IB Physics 1-2 kids. All right, so this acts on protons only in the nucleus because protons are the only thing with any charge in the nucleus. And it's repulsive, right? Those protons in the nucleus don't want to be stuck in there together. They're exerting a repulsive force on each other, okay? And it's a pretty small force, but not insignificant, right? So there's this relative strength row here, where if the strong nuclear force that I'll introduce in a second has a strength of 1, the electromagnetic force has a strength of 1/37th. Okay, but the weak nuclear force has a strength of 1/1,000,000th. So that's why it's called the weak nuclear force, because it's really weak. Anywho, so let's talk about the strong nuclear force. That acts on any nucleon, a proton or a neutron. It's attractive. It's very strong, right? Hence its name. But it's got a short range, right? The strong nuclear force has a range that's only big enough to like hold a nucleus together. So like electromagnetic force has an infinite range. It's repulsive, but when these nucleons are really close together, the strong nuclear force comes into play and overpowers the electromagnetic force, right? Once a nucleus gets too big, right, then the strong nuclear force can't overpower the electromagnetic force, and you get some stuff happening with the nucleus where it starts to break apart, and we'll investigate how that happens later on. Okay, and then there's a weak nuclear force. It acts on protons or neutrons. It can be attractive or repulsive, and it has an even shorter range, right? So things have to be even closer together for the weak nuclear force to act. And we're going to talk about different types of nuclear decay later, but this is responsible for beta decay. For beta, that's a beta decay. And again, I just want to have that note there, but we'll go into more detail later on. Okay, so you guys remember in quantum, Rutherford did that gold foil experiment. He shot an alpha particle at some gold foil, and that helped him to realize that atoms aren't just big blobs of positive with little negative bits scattered throughout. He found that there were very, very dense regions of an atom that had the positive charge, and the rest of an atom was pretty much empty space. And so that helped us understand what an atom looked like, right, in terms of how it was built. But we're also able to see something. He was also able to calculate something else that was really interesting, which is a nuclear radius. So just remember the main results of that alpha particle gold foil experiment. Remember, most of the alpha particles were passed through the gold leaf undeflected. Some alpha particles were deflected through very wide angles, and some alpha particles rebounded in the opposite direction. The interpretations of the results were: most of the atom is empty space. The atom contains small, dense regions of electric charge. These small, dense regions are positively charged. Okay, and then we'll look a little deeper into another one of the results in a little more detail. Okay, so let's say that we have just, here, I'll draw this in black. Okay, let's say that we've got, you know what? I think I have like gold here. Oh yeah, gold. Okay, gold has a charge of 79 times the elementary charge. Okay, that's gold. And then he shot an alpha particle. Okay, that alpha particle we'll draw as black. And the alpha particle has a charge that is 2 times the elementary charge. Okay, the alpha particle had, let's say, the kinetic energy at the beginning of the alpha particle's motion as it was shot towards the gold, had a kinetic energy of 7.68 mega electron volts. Okay, and it was fired with that kinetic energy. And when he looks specifically at an instant where the alpha particle came right up to a gold nucleus and bounced back, right, directly back, that's the situation that we're looking at. So here's the alpha particle. Its kinetic energy, right at the moment that it gets as close as it possibly can to the gold, its kinetic energy is 0, right? But it has some electric potential energy because the alpha particle has been slowed down because it's being repelled by the gold itself, right? So that potential energy is equal to the kinetic energy that it initially had, which is 7.68 mega electron volts. All right. And so that energy is equal to the kinetic energy initial, which is K times alpha's charge times the gold's charge over the radius. And then we're kind of